Of PTV talks. Today I'm talking about one of the features of the latest release in Vissim 2023. We have the automatic speed limitation in curves, and I want to present you some background and application. And the reason why I do this is that during the time when we developed the feature, I got aware that there might be quite some potential for misinterpretations and misunderstandings. It might sound a bit strange possibly at first, because it seems it's quite a simple topic, but in fact there are quite some subtleties, and I'd like to present this to you to help you understand under which conditions, when you will have to change the default function of speed depending on radius, and how to do that, how to calculate different functions, and what one should have in mind when doing this, when changing this function. And I will also present the feature at some point of this talk. I will begin with basics from physics, so the centrifugal force, and then design an alignment and how there, usually it's the other way around. So radius is determined depending on design speed. Then a bit on perceived safety limits of real drivers. Then next, the effect of a legal speed limit, and then showing the feature in Vissim. And then finally the default functions. Why are they how they are, or the one single default function for cars speeding curves. How did I compute this, and when would you have to change it? Physics. Flying chairs. Flying chairs is a good example, because there the angle of the chairs which is required is automatically showing, whereas when we are cyclists or motorcyclists, we need to do this on our own. But we have a very good intuition for that. And in first approximation, I mean, there are many details and aspects on this when you're steering, which make this in effect quite complicated. But in first approximation, you have the centrifugal force from driving the curve, you have the gravitational force, you imagine both attacking at the center of mass of the driver, and then the sum of the two forces must point to where the wheel touches the ground, and that gives the angle of which the driver has to take or has to lean to neither fall to the outer side nor to the ground. That's the angle. So the phi angle is the tangents of the phi angle is the centrifugal over the gravitational force, and that works fine as long as the friction force on the ground can be large enough to compensate the centrifugal force. By definition, the friction force is the gravitational force times some friction factor, friction coefficient mu, and obviously that tangents phi must be smaller than mu, because you have both at the same position of the otherwise identical equation. And this tells us how fast at maximum as cyclists or motorcyclists we can drive through a curve. In terms of charts or speed versus radius, it looks like that. So you have a square root function, exactly a square root function in that simple physics picture, where the lateral acceleration, depending on radius, is just a constant, and the constant depends on the friction coefficient. Or, I mean, you can, of course, usually you drive with enormous safety factors. So it depends on how close you want to get to that limit. Now going to four-wheelers, vehicles, they must fulfill two conditions to drive safely, and that is, they must not slip from the road, and they must not roll over. The first condition, that they must not slip off the road, since they have four wheels, they have an advantage over the two-wheelers. The contact area with the ground is larger, and that means that the total friction force is a bit higher than for two-wheelers. So in principle, cars could go faster in curves than motorcycles. So that is shifted to higher values. If normal drivers do that, in fact, if they make use of it, that's a different question, but from a physics point of view, they could. The other condition, that they must not roll over, is such that, I mean, that's where the cyclist leans into the curve. A car cannot lean into the curve, but instead it has two touching points to the ground. So the two tires touch the ground at a different position compared to just the vertical projection to the ground of the center of mass. And usually when you do this calculation, that you have the gravitational force and you have the centrifugal force, and then the condition is that the sum of forces must touch the ground or point to a point on the ground which is between the tires. If it's outside the tires, the car would roll over. And when you do the calculations and you calculate this so-called safety stability factor, which is relating the track width of the car, so the distance of the tires, if you want, and the height of the center of mass above ground, then you will realize that cars would rather slip from the road than roll over, which is good, because slipping off the road is already not good, but rolling over is worse. It's a different thing for loaded trucks, where the center of mass, the center of gravity, is can be at quite high, can have a high value, especially say a loaded firefighting truck which is loaded with water. There it's very high, and these drivers must be quite careful, which is a challenge because often they are pressed to get to the point, to the burning building, but they must take the time to not roll over in curves. If you are interested in that topic, the United States NHTSA agency is calculating for each vehicle type which is allowed to be sold in the United States. They calculate this safety stability factor, and here you see the ranges. And for cars, the chance to roll over is very low. It has many safety stars. For vans and pickups, it's higher, and the SUVs, there is a wide range. So if you're considering to buy one, check this webpage. Otherwise, I mean, if you're Googling for car rolling over and SUV rolling over, although the SUVs have a comparatively short history, even considering the also quite short existence of the internet, they have quite many, a relatively high number of search results. So yeah, and trucks, it would be, especially loaded trucks, it would be even higher. Also take care what I said, it's all again a simplified physics picture. From the driving dynamics, different conclusions can follow with a much more complicated physics. And then even if this safety stability factor is higher than the friction factor, it may happen that a car or a truck or a pickup rolls over. Then we have, of course, for roads usually a super elevation, a cross slope, which mostly is in favor of the driver in curves. Sometimes that cannot be implemented, but in really most cases it helps, like it helps the cyclists. So it's leaning to the outside of the curve, so the outer side of the curve is higher. And then in this way, the geometry of the road is taking some of the centrifugal force and is leaving only a smaller part for the friction force, so the car does not roll over or slip off the road. And the formula is just modified in this way that the incline, so if it's 5% incline, it's a 0.05 here for the Q, is adding to the new to the friction factor. So that's again looking at this. So how can you envision that? If there is no super elevation, it looks like that. So that's the picture from before. And then if we have a super elevation, the picture changes like that, and you see that the point where the resulting force is touching the ground is going more to the center of the car. So here, and then it's moving to the inside. Good, that's it with the simplified physics picture. For design and alignment of roads, it's a bit more complex, the physics which is being considered, since there the engineers are considering that the friction is reduced for higher speed. So that's from a German publication that says speed in kilometers per hour, and that's the friction coefficient. And while on a dry surface, the friction coefficient is really high, almost a 1, or it can be a 1, or even higher when you have some additional technical factors. But on a wet road, and roads are designed for wet and clean roads. I mean, it's a national thing. Yeah, it might not be like that in every nation around the world. I cannot guarantee that, but my research went into my literature research into the German guidelines, French guidelines, Swiss guidelines, and I always found it's designed for wet and clean roads. With high safety margins. What does high safety margins here mean? So kind of 40 years ago, some engineers measured the friction between tire and road. For different tires, I think maybe also different types of asphalt. And then they take the 95% line. What does that mean? That it means that in 95% of cases, the car would not have slipped off the road. Yeah? And that friction factor or friction coefficient they take to design roads. By the way, that means iced road, flat ice. So a wet road can, for bad tires, it can go to quite low values at higher speeds. And from that 95%, there is still usually a safety factor, another safety factor of 50% or even 60% of friction, which is by which the assumed friction is reduced. And then this is taken to tell the radius must be so and so large if the road is designed for this or that speed. And then from that dependence, friction coefficient in dependence of radius, we get these functions. And that's not all. So we don't, or the designers usually in different nations, they don't have a continuum, but there is a small set of road categories. So roads are categorized. You see that here, yeah, for design speeds. So for example, a minor autobahn in Germany would have a design speed of 110 kilometers per hour. And then this is taken as ground to tell the radius. Just a side note, I mean, everyone knows in Germany you can go as fast as you want on highways, at least at certain sections. But the design speed is, to the best of my knowledge, never higher than 130 kilometers per hour. So if you drive faster, it means you're making use of safety factors and you're above the specification speed of the road. And usually people don't use technical systems on a normal basis outside the specification range. So take care. And then the next step, which is usually done, and again, it's a national thing, yeah, it might be different in your country, is that a maximum super elevation is defined, and that's for the rural roads in Germany, 7% cross slope. And then it is checked, what is the smallest radius where with the largest allowed super elevation, we still can go safely with the safety factors, safety margins, safely through the curve at design speed. And when the radius is larger, then typically the super elevation is reduced. Why? I mean, it could be on one day that there is a congestion on an iced road and then the cars would just slide off the road. So the preferred super elevation typically is 2.5%. There must be some super elevation, otherwise we would have rainwater there in much higher amounts, which is also a safety issue. So the preferred super elevation is usually 2.5%. And therefore, when it's possible to have a higher radius than that minimum radius, then the super elevation is reduced. And here you see that's two of these super elevation depending on radius functions for one category of roads. RAL means that it's for the rural roads, Landstraßen L, and that's for the free link or the link, and the dashed line is inside the nodes. Yeah, when you have curves inside the nodes, and there typically there is a speed limit applied of 70 kilometers per hour, and therefore you can go to smaller radiuses. Now, if we take this into account, that over the radii the super elevation is reduced, then we get a modification of the speed depending on radius function. And that's the yellow line here. Yeah, at first it's parallel to the blue line, which has a high super elevation. And then beginning with that radius where super elevation starts to dwindle, then it's changing and going towards the other curve, which has 2.5% super elevation only. As I said, it's national work. Here is a chart which I found. I mean, it's from 1978. It's not like that anymore today because I think there was some convergence as the engineers in various nations look to each other. But you can see that at that time in Germany, they assumed they required quite large radii compared to other nations, and especially in Sweden, they were quite optimistic that you can go through a curve of, say, 200 or 300 meters radius with 100 kilometers per hour. That's not necessarily that it means in Sweden it was less safe. If at that time on their rural roads they already had the requirement to have direction or central barriers, so separation of directions, and it was not possible to overtake on the opposing lane, then that might have been that this was their safety measure, and in turn they allowed to go faster. So you always have to consider the entire guideline and not only the speed depending on radius to make an assessment of safety. But in fact, there are some differences or some differences in these functions. So here you have it the other way around, radius depending on speed, design speed. Because at that time, 1997, these researchers found, Brilon and Grammes found that in different nations, different dependence of the friction coefficient on speed were assumed. And that was a time when in Germany they got more optimistic. They changed from blue to red, but it was still more pessimistic than in other countries at that time. And that results in different radius speed dependencies. And if you compare these functions, speed depending on radius, the simple physics picture, so that's friction plus cross slope is 0.2, which is a careful approach, including all safety factors really with what you find in the guidelines. Then you find that the guideline compared to that choice at first for small radii is more optimistic, and then it gets more and more pessimistic. And they're at that point where super elevation falls down for the first time to 2.5%. You have this bend. Fine, that's the design and guidelines, but it does tell us nothing about how real drivers drive. And that's really a different thing if we look at that function here. How was this function obtained? Two researchers, Schimmelpfennig and Nackenhorst, in 1985 did an experiment. So it was on a road or on roads or on a track, but it was in the sense a lab experiment, as the participants knew they were driving for science, so they knew they were observed. And they measured speed of the car, and they measured a lateral acceleration on the driver, so lateral acceleration inside the car, which means that the cross slope is included. If the car would stand still on a road with cross slope, the value here would be negative. At zero, it would be negative with a small value, of course. And then they found this function. So there is quite some dynamics of the lateral acceleration over various speeds. And let's, or first to do some first conclusions. That's my conclusion, my personal conclusion from looking at that chart, because real drivers are so far away from the physical safety limit at that time already. And this comes from our intuitive driving. It doesn't come from a technical system. It doesn't come from something telling us to drive slower, or that we learn something and do it consciously, but it's from a feeling in the stomach. Ooh, it takes me too much to to decide driving that speed in a curve. I would conclude that technical improvements which happened since that time, so the tire skid resistance, the friction factor was improved, I guess. Also, electronic stability program was introduced since then. that all this for most drivers in most situations has no effect, because we are driving safely anyway. And it means that likely since that time, although this data is 40 years old, it's still valid, because the feeling in the stomach has not changed probably. It doesn't depend on sitting in a car of that time compared to sitting in a car now. It might be different for the fastest drivers, yeah, professional drivers, they who use the technical abilities, but that's not what we do the traffic planning for. Good. Okay, something's wrong here on that slide. I have no idea why it's shown 2 times. I rearranged that function in a first step. Yeah, here you see this value here, and it's a bit unclear if you prefer to work with miles per hour, or instead of having here the meters per second square, you prefer to have feet per minute square. Then it's a bit hard to get it right. Whereas when you write this function in this form, you have these 2 parameters, constant factors, A0 and V0. You just recalculate the 70 kilometers per hour to miles per hour or meters per second, yeah, and then you can use the formula with values in units of your preferred choice. It's possible to resolve that equation for radius depending on speed. Then we get another of these constants, which is about 35 meters, and which relates to the other 2 constants in this way. It is also possible to rewrite that in our preferred form, namely speed depending on radius, but it looks a bit awkward, including the Lambert W function, which is essentially the logarithm, but not of the normal e to x, but x times e to x. And that's a bit difficult to work with, yeah, because you need to search where you find a system which computes that. It's not there by default in Excel, but Wolfram Alpha, for example, can do it. And you will later see it's not relevant, because we have an even more complicated form, since if you want to consider cross slope in this function, then it's not possible at all to have a closed analytical formulation of speed depending on radius. And I will later show you what can be done in this case. Here is how the Schimmelpfennig-Nackenhorst function would look like if you consider cross slope values, different cross slope values, so with 7%, or even 2.5%, but in the wrong direction, and the green line is when it's flat. And here again, or not again, but the cross or the lateral acceleration, depending on radius, you find that the highest value is at a radius of around 43 meters, assuming 0 cross slope. I forgot to say one important thing. These drivers in that experiment by Schimmelpfennig and Nackenhorst, they were told to drive so fast that they still feel it to be safe. Which means these participants, they were aware they are being observed. They were given the task of driving fast, but still safe. And that is different to what we do normally. First, they did not have a legal speed limit in mind, especially not a general speed limit, like here, you see it here for Hungary. And second, they always had in their mind, let's go fast, let's go fast, let's go fast, just not too fast. And normally we know, okay, we already are at 90% of the legal speed. And we don't always think about, or most drivers don't always think about, how fast can I go through this curve. So what would be interesting to have is observation data of drivers who were not aware that they're being observed. And that exists. It's from 1978. I have previously already here in this talk cited that publication, and Lindenmann and Ranft in 1978, motivated by the recent introduction of a speed limit of 100 kilometers per hour on rural roads. They measured speed in curves, and that even at different points of the curve, yeah, at the beginning, in the center, and at the end. They measured it for both directions, and they gave even the cumulative distributions of these speeds. So they gave the 15% value, the 85% value, so the 85% fastest driver, average value or 50% value. And that for these curves here, which are documented in all details, individually for the curves, including or giving the radius also. And that's what it looks like. So the points are their results. So the average, oh, no, that's not the average, but the 85 percentile speed value of drivers in one particular curve. That's one point here. And they postulated that this scattered data should be described analytically as an average function with this function. So some speed value divided by 1 plus some constant times radius to the minus 1.11. Alternatively, that's the first step. It doesn't change anything. Yeah, using this alternative function always gives the same result. I just include this parameter in or I include it with the exponent. So 40.62 to 1.11 is 61.05. And in this way, this constant has a good unit, namely meters, instead of meters to the 1.11, which doesn't make a lot of sense. And it has a meaning, namely that at a radius of 40.6 meters, the speed is half of this maximum speed of 105, because then we have 1 plus 1 in the denominator. So the same for the average values or the 50% values. And you already here see an advantage of including this parameter with the exponent, namely that it's much closer to the one of 85%, or almost identical. So it seems that these curves in effect are more similar than it seems initially. We don't have different parameters for different percentiles, but only two of the parameters appear to have different values. Then I observed a problem with these two functions, namely that at small radii, smaller than 14 meters, the 85% speed gets smaller than the average speed. That's of course nonsense. And the other problem I had is that Lindenmann and Ranft, they didn't give a function for the 15% value. But of course, while for safety considerations, the fast drivers are most relevant, for traffic planning, it's the slower drivers who might, they cause delays for other drivers. So I had to come up with a solution for the 15% speed anyway, and I had this problem. So I did the search for good values of these three parameters for the three cases, 85%, average speed, and 15%. I did it for myself, and since this search was not documented in the paper, while all data is documented, but not this approach, I resulted with different parameters. So I used this approach, so similar to the one of Lindenmann and Ranft, and I wrote it just the same equation in this way. And if this potential law is correct, then having the logarithm on both sides should allow to place the data points on a straight line if the potential law really has a meaning, and if we find the value of parameter v infinitely, which produces the linear ordering of the data points. And as you see, it is possible. A second advantage is that while in the normal display we have the data points crammed, or almost all data points crammed to radiuses below 300 meters, and then outliers at very large radii, while in logarithmic display it's almost equally distributed, which gives a more balanced weight to the values when doing the trend line. So it's two advantages. Using the logarithmic picture and doing the trend or obtaining the trend line there. So I did that and just tried various v infinite values until I found a maximized r squared value. And then I used the v infinitely and c and RH value, which resulted in this approach. The modification is not so large, so that's the original. Blue is original, red is the corrected value. For average speeds, it's even smaller, the difference. So old is that, new is that. And here is the result for 15%, which wasn't present at all in the original paper. And placing the three new functions next to each other, we see that the radius constant is in fact similar for all, but now also the exponent is similar for all three cases. So they are different in effect only for the speed constant in the denominator. You could say that for the radius constant there is a trend. The smaller the speed, the smaller this radius constant value is. But nevertheless, the values are quite close to each other, and you could just say, okay, I take the 43 meters as value for all three. And then you can analytically calculate what is the value of the largest acceleration, what is the radius where the largest acceleration or lateral acceleration occurs, and what is the speed of the largest lateral acceleration. And yeah, if we compare that to the design speed function, we see it's really different. So first, what real people drive when they are not observed and when there is a speed limit is really different compared to what is assumed, or what it's not the case that those people who design the roads assume that people follow their speed, their design speed function, but just the functions are different. The design speed function, depending on radius, is different from what people really drive on a road. And for certain radiuses, they drive faster, around 50 to 100 meter, and then they are getting more and more in the safety range. One interpretation would be that for design, it's just important to not slip off the road. Whereas the drivers, they make a more holistic calculation intuitively a more total approach, and they consider not only how likely is it that I slip off the road, but also what would happen if I slip off the road. And there, of course, the faster you are, the higher the damage would be if you slip off the road. And therefore, possibly at low speeds and narrow radiuses, narrow curves, people go beyond design speeds, and when they reach 100 kilometers per hour, they, how should I say, they accept the safety factors which are suggested by the road designers. Now, really coming to what is the effect of the speed limit. As I said, in the Schimmelpfennig and Nackenhorst experiment, the drivers were said, the participants were told, drive as fast that you still feel it to be safe. So that's more this situation. Yeah? The race drivers, maybe not, they were normal drivers. They were not the participants of Schimmelpfennig and Nackenhorst, they were not professional drivers, but just the mindset which they had was more like that. Whereas the Lindenmann and Ranft drivers who they observed were rather in this mindset, yeah, normal, thinking about something, being bored, being annoyed, and intuitively accelerating or taking the foot off the gas pedal. And that's different, yeah. So if you, the next time you drive a car and you have the default function in mind, which is proposed in Vissim now, and you think, but I think it's possible to go faster through that curve. You might have some curve in mind which you find challenging in a way, and you tried it. Yes, it's possible to go faster through a curve. As soon as you try to figure out how fast can you go through a curve, you will be faster than the default in Vissim. But the default in Vissim is made for people who do not try to figure out how fast you can go, but it's made for how people usually go when they think about something else or do not think at all about anything. And that is, and the second thing is, it's made, yeah, okay, no, sorry, pardon. And now we look at the effect of the speed limit on the drivers. And there, it's at first, when we compare Schimmelpfennig and Nackenhorst, that's the blue curve, with the three curves of Lindenmann and Ranft, we see that the Schimmelpfennig and Nackenhorst curve function has a good agreement with the 85% function of Lindenmann and Ranft up to a radius of 250 meters. Yeah? And then the Schimmelpfennig and Nackenhorst drivers are faster. By and by they get faster, whereas the Lindenmann and Ranft drivers by and by approach to the speed limit, eventually even going a bit faster than the speed limit is. But obviously, it seems like the speed limit is casting a shadow to speeds which are just a bit smaller than the speed limit. At that point, at 90 kilometers per hour, it seems that normal drivers who are not observed already do not accelerate so much anymore if there is a speed limit of 100 kilometers per hour. And that gives this discrepancy. Yeah? I mean, we have that this 110, that's the value of this constant in the Lindenmann and Ranft function for the 85% drivers. So where we would assume, which is reached by those drivers on a really straight road. And they reach that with respect to radius slowly compared to the Schimmelpfennig and Nackenhorst drivers who were just going to higher speeds already at smaller radiuses, at least if the radius was larger than 250 meters. And it's really interesting because at even smaller radiuses, around 100 meters, the Lindenmann and Rand drivers were even as a little bit faster than the Schimmelpfennig and Nackenhorst drivers. Now, this description is even more true for the Lindenmann and Ranft, for the 50% drivers of Lindenmann and Ranft, where the Schimmelpfennig-Nackenhorst function is correct only up to, is a good description only up to, say, 70-meter radius, which is quite narrow. And the 50% drivers, they are slower than the Schimmelpfennig and Nackenhorst drivers at a radius like kind of, don't know, 20, 25 meters already. So they are really, really slower than the drivers in the Schimmelpfennig-Nackenhorst experiment. But that's really no surprise. I mean, in that experiment of Schimmelpfennig, the drivers were told to go as fast as they just feel to be safe. And second, I think, if I understood correctly, Lindenmann and Ranft also included drugs in their evaluation, and drugs were not present in the Schimmelpfennig-Nackenhorst experiment. So that's something also you have to have in mind, that when you use that is in Vissim for a simulation, that possibly, so if you have cars and trucks as separate vehicle types, that possibly the cars would go faster at a certain, or the slowest cars would go faster at a certain radius, but then you have the trucks and the trucks might be slower. Good. So that's another written summary of what I said, describing these charts, describing the functions. And the next step is to show you the feature in Vissim. I've prepared a model for that, the same model twice, always for comparison. This one, the upper one, will remain unmodified when I present it to you. And whatever I modify, I will do in the lower loop here. Good. Here it is. So that's the model. And yeah, let's have a look. So here they are, and you see them approaching with a high speed. So they're shown in green, and then they brake already, because here is also a curvature, a curve. And then inside the loop, which has a diameter of 120 meters, so 60-meter radius, they are slower, much slower than this normal desired speed. And then they leave and re-accelerate. And that's really, so there is no reduced speed zone present, as you see here. And that becomes even more clear when I show you the first option you have. You can switch off that new feature entirely. That's for compatibility with old models. So when you have an old model, you still can load it to Vissim 23 and then have the old behavior. And there you see they will stay green. Sorry. Base data network settings now. So it switched off, and you will see they now will stay green. Whoosh. So quite fast. Good. That's one parameter you have in which is related with that feature. The next one is the curve speed functions. So they are here, base data functions, curve speed. And with the defaults INPX, there is one for each vehicle type, which we have. And these functions are used with the vehicle types. So there is this new parameter, which gives the desired curve speed function, which is used for that vehicle type. There is no local desired curve speed function. We chose to not have that. Like you could have a link behavior type which also has a desired curve speed function that is not present, but what you can do is first again run the simulation to see that the feature is active again. Oh, you already see them breaking. But what you can do is switch off this for each and every point of a link. And if we do that, our drivers will not stay as fast as if the feature was disabled, because they will brake for the connector. But once they are in the loop, they accelerate, yellow, and then they brake for the next connector. And the next thing you can do, and I need first to activate that again, is that the radius, so each of these link points has a radius, and we can say one of these should not be calculated, but I want to give it myself 20 meters. Sorry, let's keep this showing the point. And then drivers will brake for that point as if the radius there would be 20 meters. That is there because it's sometimes when you modeling manually, not importing from somewhere, also not creating a circular link with the assisting tool, then it can be difficult to get to model it such that you get the radius which you want to have, which you might know explicitly from planning documents. And then you can just override the calculated value. Yeah, that's it. These are the parameters to control this new feature. And so we can go to the default function or default functions. There is one for each vehicle type, and how they were calculated and what was assumed for that. So the strategy now is for the defaults at least that we use the original Schimmelpfennig and Nackenhorst data as Vmax. For them, it was the 85% driver, but we use it as upper speed limit. And then, of course, individual desired speeds may cap that. If a curve speed is computed to be higher than the desired speed of that car is anyway, then of course the car does not speed up, but stays at its desired speed. Then we use data from Lindenmann and Ranft, and that's the data for the very narrow curve with small speeds, to compute Schimmelpfennig-Nackenhorst functions for average speed and minimum speed. Why that? Why don't we use Lindenmann and Ranft directly? Because there was an explicit speed limit of 100 kilometers per hour %. And that might underestimate speeds if there is no speed limit or a higher speed limit. So the defaults in Vissim assume there is no speed limit %. And that means for mid radius values like 200 meters, 100 meters, drivers might be too fast, but then at higher speeds, their normal desired speed caps the curve speed function. So that's one approach. You can choose against that. You can say, I'm computing or I'm simulating an urban setting, and there is a speed limit of say 50 kilometers per hour. And then you define your own speed functions for that particular project. But as a default, we have this different approach. Yeah? And then as a third step, because we want default functions for different road categories, yeah, from urban to Autobahn. I'm calculating these functions with different cross slopes assumed and integrate the resulting 3 or 4 functions into one function, because speeds of 50 kilometer per hour or 30 kilometer per hour and radius of 15 meters is relevant in urban settings, whereas speeds of 100 kilometer per hour, that's not relevant in urban settings, but at the highway, and there I assume the highway cross slope. So that's the 4th step already. And yeah, then of course, we need to do that for all 3, average, minimum, and maximum. And the minimum and maximum, they are mapped from Lindenmann and Ranft, 15% and 85%. Yeah? Good. So use original, that's the first step, use original Schimmelpfennig and Nackenhorst data as maximum curve speed function. So that's quite simple, as I said, because we already have that function. Yeah, we just take that and we don't need to look at the Lindenmann and Ranft. That's trivial. What is not trivial is that Schimmelpfennig and Nackenhorst, they had this, as I said, they had the cross slope implicit, yeah, and we need to make it explicit because we want to include our 6%, which are defined for German Autobahn as maximum cross slope. And then we need to modify Schimmelpfennig and Nackenhorst function with that in mind. And we will see later how this can be done, because it's a bit challenging, as I said, because there is no closed form for expression which does that. Later more on that. Good. But now for the other 2, the central function for average speeds and the lower limit minimum curve speed function. Identify a suitable subset of the Lindenmann data. Speed should be small enough so we can assume that they were not affected by the speed limit. The turning angle should be around 90 degrees of the curve, because yeah, some standard, huh? Not too small, not too large. There should be no visual occlusion from which one would think that it may have slowed down drivers even more, because in Vissim we don't want that. If you know in that curve there is a tremendous occlusion, yeah, really a building to the edge of the road, and drivers cannot look what's behind, and therefore they drive slower, then you need reduced speed zones still. Good. So 3 conditions, we need to check that. And for the first curve with 20 meters radius, obviously cars were slow enough. There was only a moderate occlusion, and the angle is fine. Yeah, 123 degrees. Good. The second curve also was quite fine. Moderate occlusion only, good angle. Speeds below half of the speed limit, still good. And then the third curve already of those many curves which Lindenmann and Ranft measured, the angle is too small. I mean, 25 degrees, that's even though the radius is quite small, but it's only a deflection of 25 degrees. So I chose to ignore that. And then the next 2 curves, it showed later on in the data that these 2 are below the general trend of the data, and therefore I omitted these as well. And all others, the radius is too small, the speed is too high, and so they could have been considered. Look at that road here. It's just one can assume that here the general speed limit of 100 kilometers per hour played quite some role in slowing down drivers compared to drivers who would drive without such a speed limit. Good. So we are left with only few data, and here included is even still data from those two curves where I was not sure if there is occlusion which slows down drivers. But as I said, they fall below the general trend. So all other data of the next larger radius curves is at higher values. And so I omitted these as well. Then the next step is at those slow speeds and small radiuses, it plays a role, I think, that the inner lane has a smaller radius than the outer lane. And Lindman and Ranft didn't do a correction for that. I did here. So what was here at the same radius value here is at two different values. The inner lane is at smaller values and the outer lane is at larger values. The same shown not with speed versus radius, but with acceleration versus radius. So that's more the, no, sorry. And then, so we need that lateral acceleration versus radius picture because we need to compute the acceleration which attacked at the car. Which the driver felt, sorry. To compare it with Schimmelpfennig, we need to compute the acceleration which the driver felt, because this acceleration is computed from speed squared divided by radius. But that's the lateral acceleration which attacks at the car, and the cross slope of the road takes some of this lateral acceleration. And to compare it with Schimmelpfennig and Ranft, we need to have the sum of the centrifugal force reduced by the cross slope gravitational force component. And now having that, we can now compare this slightly modified Lindenmann and Ranft data with Schimmelpfennig and Nackenhorst, and we see that in fact for this speed range 20 kilometers per hour up to 40, 45, it matches relatively well with the Lindenmann and Ranft. Schimmelpfennig and Lindenmann and Ranft match quite well for the 85, so for the fastest drivers. And that's what we would have expected, because Schimmelpfennig and Nackenhorst told them to drive fast, and Lindenmann and Ranft, we have here the 85%. And now we do a really optimistic step and by saying there where the agreement of the trend line, and the trend line is only from 3 data points for each of the 3 speeds, there where the agreement of the 85% is best with Schimmelpfennig and Nackenhorst, there we compute the parameter values for average speed and minimum or 15% speed with Lindenmann and Ranft speed as basis, but for the Schimmelpfennig-Nackenhorst function. Why? Because we want Schimmelpfennig-Nackenhorst function as we assume this is the function which describes drivers who do not have a speed limit in mind. And that's the result. So where we have the 10.85 A0 parameter value for the 85% drivers, we have 9.49 for the average drivers, average speeds, and 7.27 meters per second square for the 15% or minimum speeds. We want to use it as minimum speeds. And so the assumption here, which is used here, is that the exponent and the V0 both keep their value, and only the A0 parameter is scaled to describe the slower cars. If we would vary this as well, we would need more information. That's the first thing. And second, from the functional form, it would easily happen that again these functions intersect, and then the 15% drivers are once more faster than the 85% drivers, which is of course nonsense. It's not only unrealistic, but it's really nonsense. And scaling only the A0, this is not possible because it's just a general scaling factor. Modifying only a general scaling factor makes the difference between the three speed percentiles a bit trivial, but the trivials aspect it's good because they don't intersect. If it's non-trivial, then they would intersect. So that's how it looks like. So we have here the lateral acceleration depending on speed. So exactly the Schimmelpfennig-Nackenhorst picture for 85 percentile, average speeds, and 15 percentile. Looking at this very same function in the speed versus radius picture, the difference doesn't appear to be so large, but it's really the same data. Yeah. So you see how little speed differences. I mean, that's also going to radius of 5,000 meters. How little a speed difference of which you barely can see here because the radius is so large, what effect it has on lateral acceleration. Now zooming in the speed versus radius on rural roads, 500 meters, it looks like that. There already you see it seems like there is a larger difference between the three percentiles. And zooming in on rural roads, it looks even larger. So here is the 50 meters where about the maximum lateral acceleration occurs. Now, back to this challenge of inverting a function. So far, when I have presented to you these functions, I could do so because at that point I didn't need to formulate it for Vissim. And I had it in the form radius depending on speed. You can plot that, although I had the data in the form radius depending on speed. In the chart, you can show it nevertheless like speed depending on radius. But as you see here, the data is aligned here horizontally. That's what I mean with I have a function radius depending on speed. There is one speed, 30 kilometers per hour, and then there is a function which gives the radius for the 85%, for the central value, and for the 15%. But what we need for Vissim is the other way around. There is one radius, and I compute three speeds from that. As I said, for zero cross slope, in principle, there is an analytical closed form function, and then you can directly calculate that. But as soon as there is a cross slope, that's not possible, and we need to numerically invert these functions. And inverting a function numerically, you can do in many different ways. You can write a script which does it. You can apply a rigid mathematical method for that. I would like to show you to enable everyone really, also the people who are not able to do scripting, to do programming. and don't have a computer algebra system available, I want to show you how you can do it in Excel. Just to give everyone at hand a way to do that. And that's here. So in that sheet, you see what I did is calculating for speeds in steps of 1 kilometer per hour first, the net acceleration with the Schimmelpfennig-Nackenhorst function. So here, what is shown yellow here is the functions which are behind these numbers. So you see here what you need to code to do so, which means that's the acceleration which the driver felt measured by Schimmelpfennig-Nackenhorst. But that's not the lateral acceleration which really attacked at the car, because for that we need to consider the cross slope. So the lateral acceleration which attacks at the car is increased. It's larger than what the driver feels. So therefore plus cross slope times 9.81. And from that, then I can compute the radius from the total lateral acceleration and the speed which was driven. I can calculate the radius of the curve. Now I write in another column exactly those radiuses which I want to use in Vissim for the curve speed function. And then there is this xlookup function, which says go to column G, use that value and search in column E for the value which is the next smallest. Smallest is here the -1, and use that as value here. You can do the same for the next larger value. So these two are here. That's the +1 versus the -1. -1 is next smaller, +1 is next larger. And you can do so saying, go to column G, use that to search the next smaller value in column E, but don't give me that next smaller value, but give me the value which is in the same line in column B. So therefore we have here the 11 and the 12 for these two. And there you see, for that reason, you have the E here twice, and here you have the E only once, and instead in the second place, the B. And finally, I simply do an interpolation here. So that's shown here. Depending on how close or far away these two values are from the true value here, I interpolate the speed between 11 and 12, and that results here. And then, of course, since we have the closed form for the calculation in the other direction from speed to radius, we can do a verification and compute from our speed the radius. And you see it's exact up to the third position after the comma for the first 3 radiuses. And then you see the first very small difference to the input value. It's really minor. I'm sure Lindenmann and Ranf didn't measure the radius of the curves where they took their data in that precision. Good. Now we have another problem. I showed you before that for one and the same class of roads, category of roads, different cross slopes are being used. So for the highest design category of Autobahn in Germany, the cross slope varies between 2.5 and 6%. That's shown here. Minimum cross slope, maximum cross slope. And in the charts in these guidelines, cross slope is given depending on radius. And that is a problem because to calculate radius in our formula here, we need to have cross slope. But to calculate cross slope, we need to know radius, but we don't have it. We first need to calculate it here. And here I did another simplification because, I mean, of course, you can do that strictly mathematically. It's possible. But to be able to stick with Excel, I did a simplification. Instead of linearly changing cross slope with increasing radius from 6 to 2.5%, I first once calculated the speeds for cross slope of 6%, then I calculated speeds for a cross slope of 2.5%. Then I had the two speeds, one for 6% and the other for 2.5%. And I interpolated the speeds linearly with the radius. I interpolated the speed between those two speeds linearly over the radius, over increasing radius. That gives slightly different results, but again, I guess at other points of this formalism, we did larger mistakes. Good. So here we have our average speed depending on radius for different road categories. Blue is urban. We can stop at 100 kilometers per hour because hopefully no one drives faster in an urban setting. Then we have the rural roads, which go to some higher values. I mean, both are extending to values which do not occur usually, but just to be safe. And then we have an urban highway. That's something which is a bit special, I think, in Germany to have urban highways. And then we have the Bundesfernstraße, Bundesfernautobahn, so the usual highway, the usual Autobahn, where it's true that at certain sections you can drive at speeds that you find to be safe. And that gives these four functions, curve speed functions, and these are included not in the defaults IMPX because we didn't want to have a long list of functions, but these are included in examples which are installed with the setup, beginning with some service pack of 2023. So you can open these and copy them or read additionally only the curve speed functions, and then you have these and can use them in the project. Yeah, so and how did I do, what did I do to get from curve speed functions for many curve speed functions for many road categories to one curve speed function, which is a compromise that's shown here. It is a compromise, but actually it's not so much of a big compromise. It's less of a compromise than you would think initially. So here are the radii, which extend over the full range where this new feature is effective. If a radius is larger than 1,000 meters, the feature is not active, not effective anymore. So there is no curve speed function, no curve speed computed and no curve speed applied if the radius is 5,000 meters or 1,001 meter. And if we have a look at this, where does a radius of 5 meters occur? Does that occur on a highway? No, of course not. Even in urban settings, that's rare, but it can happen at intersections and if a car is parking into a parking lot or some other maneuvers on small spaces. And there, on such settings at intersections, we cannot assume that there is a systematic cross slope. There is a cross slope because we must get rid of the rainwater, but we cannot assume that it's in favor of the driver. So when there is no systematic cross slope, I say there is no cross slope at all. I set it to 0. And since such small radii do not really occur in different settings, we can say, okay, for the first 3 radii, the smallest ones, we assume a cross slope of 0. So we use the speed, which is calculated for a cross slope of 0 for these radii. Then we go to 60 meters. That's of course something which can can exist in an urban setting on a link, on a normal road, and there we might have a supportive cross slope of 2.5%. On urban highways and highways, we need to have, most of the time, there will be a large cross slope of 6%. So the question here is really which value would we assume that exists if the radius of a curve is 60 meters. And there I said, yeah, it's probably rare that such a radius occurs on a highway. So I take the cross slope from the urban setting. And then going to higher radiuses, I shift the compromise more and more to the highway. I mean, here it's even questionable. In urban settings, a speed of 61 kilometers per hour, that can occur, yes, if someone is speeding, or one of the arterials inside a city could also be like that, and then some cars which are a bit faster, but the effect will be small. So yeah, it's already questionable that this is still relevant for urban settings. And these considerations I do for all road categories already, and come up with this assumption of cross slope, which should be expected, likely, most likely, for such a radius. And then I use the speed, either I use an according speed according to this cross slope. And that's what you find in the defaults IMPX file as compromise and default function. Now that we have that function, we can compare it. That's of course interesting to compare that to the Lindenmann-Ranf data. And there is already some warning. If you say, okay, I have a road with a speed limit of 100 kilometers per hour. So I use desired speed function 100 with 100 kilometers per hour. And the rural roads curve speed function with number 1002. And then you see that you would get the thick red line in Vissim, which overestimates speeds considerably. And that's there you see that it's really a combination, or it's situation dependent. So the desired speed must be chosen correctly. The default in Vissim overestimates compared to the settings of the specific settings of Lindenmann and Ranf, where they did their observations. I think the 100 kilometers per hour distribution of desired speeds is fine for a highway, really. Yeah, if there is a 100 kilometer per hour speed limit, then the fastest cars really go with maybe 130. They are speeding, and it's realistic to have that. But on rural roads, rather not. And that's what Lindenmann and Ranf measured. So if you use instead, as for the average speed, if you use instead the average value which Lindenmann and Ranf measured, so the V infinite parameter value for the central function, then it's much closer to the empirical data, which is no surprise. But still, you have a range where speeds are slightly overestimated, and that's because that's due to our approach. That we use the Schimmelpfennig function, which models car drivers who do not have a speed limit in mind. Yeah? The speed limit only comes into play with the desired speed, which caps the curve speed function. If you want to consider the speed limit explicitly, then you need to modify the defaults. Similar, the slowest cars also, it's fine for the upper end, it's fine for the lower end, and in the middle there is some overestimation for the reason which I just stated. And similar for the fastest cars, yeah, there the upper end of the 100 kilometer per hour desired speed distribution is, as I said, 130 kilometers per hour. So there would really be a discrepancy. So one must use what Lindenmann and Ranft really measured in the field. Good. Trucks. Oh, trucks gave me really a hard time because trucks exist in two ways, loaded and unloaded. Unloaded trucks, empty trucks are similar to cars. Yeah, the friction between tire and road, the lateral friction, is very similar. It's not exactly as good as for cars because the tires of the trucks are harder, stiffer. So they can be used longer, and that reduces a little bit the friction. At least that was the case. Maybe meanwhile there's a technical solution for that. I don't know that, but that's what I found. And but the effect is small. Loaded trucks is a different thing. Their center of gravity, their center of mass is higher, and they might roll over. And the bad thing is, while we have an intuition for centrifugal force in relation to friction force on the ground, we don't have an intuition for rollover risk depending on how our truck is loaded. I'm personally not a truck driver, but it just feels the same. Yeah, surely. If you drive a loaded truck or not, you may feel it in the transversal acceleration along the road, but the lateral acceleration is just the same in the curve. So we may assume some drivers drive really careful a loaded truck, because they are afraid it might roll over. Some drivers drive more risky. So we have a broad distribution of speeds. Plus we have empty and we have loaded trucks, which of course widens the distribution even more, much more. And indeed, that was found in the field. That the distribution of speeds of trucks in curves is extremely wide. So it's going here in that case from 14 to 28 kilometers per hour. And I mean, computing a central value for that is, it doesn't really make sense. I mean, it looks a bit worse than it is, in fact, because the scale starts at 10 kilometers per hour. So usually it would start maybe here, yeah, but it's still a wide distribution. Since that data, which I showed on the previous slide, was obtained, things changed. So now there is the ESP, and particularly a load adaptive ESP, which means the electronic system which helps that the truck does not roll over is adapting to the load of the vehicle, how it is loaded, how much is loaded. And that means that the drivers, if they want, they can go closer to the stability limit. And I must say, I have no idea how much drivers really do that, and how much they really rely on the electronic system, unless they do an experiment and try to test the limits of the system. But so generally, what I thought is that probably the lateral acceleration compared to the radius for trucks should cap the maximum. So there where the car drivers have a high value, probably the truck drivers have a low value, and we can orient, I think, at the function, the value, the maximum value of the lower limit of the function which we obtained before. So the minimum function which we obtained before, while for larger radiuses, when the lateral acceleration is anyway smaller, we might assume that the truck drivers might rather go to higher speeds and higher lateral accelerations, because there is no rollover risk. Then when they survived this value, they would surely also drive in a stable manner at this value. And that can be done if you change the exponent to 2.15 and the V0 value to 91 kilometers per hour. That might seem counterintuitive that you have to increase that speed, but that's just a property of this function of Schimmelpfennig and Nackenhorst. And then in the speed of radius chart, we get this behavior where you see that at the lower end, the trucks are even slower. That was not intended by me when I played around with the values of this function. But I think it's still realistic because because the turning radius of trucks is larger. So for such small radiuses, trucks probably are slower because they are close to their geometric limits of turning in such a radius. Good. Limitations. Yes, of course. Data is missing for cars, even especially in urban settings. It would be great if we had some data on how do cars drive in curves at intersections, urban intersections. Some more data maybe for trucks, unloaded compared to loaded, which is hard to obtain because often you don't see if the truck is loaded or not. Then also what is particularly missing is data for on the lower end. So we have more data on the 85 percentile. There is very little on the 15 percentile. And if it is given only implicit, so you need to read it from the chart, it's not written in the paper in a numerical manner. Vissim does not, so, and the next is limitations of the feature in Vissim. It does not automatically consider effects of occlusion. If you have it, you need a reduced speed zone. It does not consider the effect of lane width. So if you have a very wide or a very narrow lane and you think for that reason drivers are faster or slower in a curve, you need to adapt the curve speed function. And it does not consider when cross slope locally does not adhere to these design rules. That should be relatively small differences, but it's not included. And due to the formalism which led finally to the default function, speeds which are around at half speed or half the value of the speed limit might be slightly overestimated in Vissim with the defaults as they're used. And another thing which is not being considered is effects of aerodynamics. So if you have such a race car which just in effect doubles the weight of the car 2G and therefore can go faster through curves with in some cases really enormous lateral accelerations, then of course you need to do something, probably just switch off the effect of this new feature because these cars are just fast in curves, so there is little effect. And then there are some special issues like, and that's again an example from Germany, that inside urban areas, vehicles which weigh more than 3.5 tons, when they turn right, they need to go with walking speed. If on their lane or on the neighboring lane, there could be cyclists or pedestrians. And it's, of course, a logic construct and conditions, 3, 4, 5 conditions, which cannot be considered automatically. But you have to identify such a spot and then place a reduced speed zone there. Cyclists, a few words on cyclists. Cyclists is another topic where data is missing. If you find data, it's sometimes, here it's written design speeds from free driving cyclists. So is it now design speed or was it obtained in the field? I don't know. So
there is just enough data to formulate such a function with big insecurity, not knowing if it's right. But the biggest issue is that cyclists are small compared to lanes which are usually available. I'm not talking about the lanes which we see here, where a professional cyclist on a closed lane is going downhill and is using the entire width of the entire road. But even in normal settings, cyclists often have the opportunity to sway, and by that having effectively a smaller radius. So that's shown here. Having effectively a larger radius, sorry, that's shown here. And here you can calculate that if the cyclist really uses the full width of this lane on both sides, that then the radius would be 5.8 times larger than the inner radius here. And that would mean that you just shift the function. You shift the entire function parallel to smaller radius values. But in Vissim, the difference is not so much large because the radius anyway is calculated not for the inner radius, but for the middle line. So we have anyway a larger radius than a cyclist who is driving on the right side of the inner lane would go. So we anyway use a larger radius value, which implicitly already assumes, if you want, that the cyclist is swaying a little bit. But still, if here we assume in a 90-degree turn, 90-degree curve, the cyclist is swaying by 1 meter, then still the radius would have to be increased by a small amount compared to the radius of the middle line. Yeah. So here is the circle which has the radius, the inner radius of the lane. This is the circle which has the radius of the middle line of the curve, and this is the circle which has the radius of the cyclist who is swaying out 1 meter. And that's of course a pity because the cyclist speed in curves is completely depending on the deflection angle of the curve and how much the cyclist wants and can sway out. And that's not how the feature works in Vissim. But on the other hand, since cyclists are usually slow anyway, yeah, compared to cars, and the roads are wide, in most cases, I would think that cyclists are reduce their speed only very little because there is a curve. So the effect is probably small. And when the effect as such is small, of course, the mistake is also small when you don't really hit the right point with the curve speed function. Now for rail, rail is a different thing, of course. They cannot slip, they just can roll over, but that's all irrelevant because what is determining lateral acceleration, design lateral acceleration for rail is that it's uncomfortable for passengers, and that's at much smaller values than when the train would roll over. For heavy rail, long distance rail, high speed rail, there is a design speed and the rail is really going with that speed, and we know that it is safe. So it's a bit trivial, yeah. It's not with the like with the cars where the road is built and we don't know what the car drivers do, and everyone does a different thing. But it's a centralized system and everyone is following the rules. And I mean, there is a function square root from r divided by radius divided by some value. And then we have the super elevation plus the super elevation missing factor, which is so the gross the lateral acceleration which the passengers feel is translated into a super elevation, an additional super elevation, which is missing, which would be required such that the passengers would not feel any lateral acceleration. That's what the formula here says. And the two values are that the real super elevation has a maximum of 160 millimeters, and the UF, so what the passengers in the end feel, has a maximum of 150 millimeters. And then additionally for very small radiuses, it's reduced. Yeah, the UF is reduced, and with that we end up with these functions where for minimum, average, and maximum I have used just the three different values for UF. It's you could say, I don't know. Probably one has to change that if you do really a project according to the rules which are assumed in the planning project. For light rail, it's quite the same. The formula looks pretty similar. Yeah, again, we have the 11.8 in a denominator. We have the 150 and so on. The guideline where you find that is TR-Trasierung, which was, as far as I know, adopted by the European Union for all member states. And here at that link, you find it in 20-something languages for that reason. The difference for light rail, I think, is that's what I guess only, that when you have a tram in a city and it's running together with the cars on the road and on an intersection, again, we cannot really assume that there is a supportive super elevation of the tracks or a significant supportive super elevation, because then the intersection would get bumpy because the tracks would be at different heights. And so for light rail, I would guess it's more likely that there is no super elevation at all in urban settings. If it's a light rail which is going out the city, then it might be different. Good. That's it. It was a long show, but now have fun using the feature, and thank you.